Hi, Physics 2, Mr. Janowski here. So this will be the last video of the year, just to kind of sum everything up. So I'm sorry this has taken so long to actually get this one up here. I had intended to do something else. I was working on slides. I wasn't happy with the way they were going. And then finally this morning, I just got an idea that I think will work better. So this is just totally optional, but just let's do a quick review of the different stuff we learned this year. All right, so again, here's this map of physics. I'll put a link to this video. If you can't tell, I really like this video. I've got the big poster in the room. We started the year with this video and discussing the different things. So yeah, it's good to, kind of zoom out, take the big view of everything that's going on. So yeah, Physics 1, we learned about half of classical physics, mostly mechanics. And then Physics 2, the plan was to do relativity and electromagnetism. So we did those pretty well. And then also get to waves, optics, and quantum physics, which we did not get to. So part of that is the pandemic's fault, and part of that is my fault, just for kind of going too slow. So maybe next year I'll tighten it up and get through a little bit more. If we didn't have the whole, remote learning stuff, we probably would have gotten into waves and optics a little bit. Maybe not with as much time as I wanted. But, this being the first year of Physics 2, I wanted to, I kind of felt my way through everything and adjusted on the fly and gave each topic as much time as I thought was appropriate. So, anyhow, yeah, we didn't get through everything I wanted, but hopefully you enjoyed the stuff we did get through. And just as a refresher, the way I, first kind of designed Physics 1, the school gave me plenty of leeway and a lot of freedom in how I wanted to teach the courses. So I designed Physics 1 to be very similar to what Physics 1 in college will be, and Physics 2 to be very similar to what Physics 2 in college will be. So my hope, this is a thought I kind of go to a lot, is that you guys, after you graduate, and so many of you are going on to do STEM things, so you will be taking Physics 1 and Physics 2 in college, that when you get to these things, they won't be totally new to you. You'll see something and it will be familiar, and hopefully you'll do pretty well with it. So yeah, anyhow, let's get going with the kind of review of things. So this review is basically going to be kind of like a lot of do now questions, just to see if you can remember the different things. So I'll read each question and then pause for a second just to give you a second to quickly answer. So yeah, we started the year with relativity, special and general relativity. So do moving clocks run faster or slower? Moving clocks run slower due to what's called time dilation. So hopefully you can remember the whole thing we did with the light clocks and all that stuff. And so yeah, this is, again, it's not an optical illusion. This is actually happening. If an observer is moving relative to you, you're going to see that observer's clock is running slower. And then related to this idea is, do distances get longer or shorter relative to a moving observer? Distances get shorter due to length contraction. So you have time dilation. Dilating is getting bigger, and length contraction. So if you're moving in a direction, that distance in the direction of your travel is going to seem shorter. So you might remember the weird thing with the train entering the tunnel, and there were guillotines on both sides. They're not shown in this picture, but the weird paradoxes. So what is the correspondence principle? The correspondence principle is that the predictions of special relativity should correspond to the predictions of classical mechanics at speeds much slower than the speed of light. So, yeah, basically we had Newton's physics for 200 plus years, and Newton's physics worked very well. So when Einstein came along and came up with special relativity and then later general relativity, which works, just very differently than Newton's ideas of things, and they're all different rules, it had to agree with what Newton had come up with, because Newton's ideas, they work really well. So yeah, the correspondence principle basically says that even though Einstein is always correct, Newton's physics is good enough if you're not going anywhere near the speed of light. And so what is the principle of equivalence? This is kind of the gist of general relativity. It's that all physical experiments conducted in a uniform gravitational field and in an accelerated frame of reference give identical results. So for example, easier to see in this picture here, if you're standing on Earth and you're not moving, you're feeling the Earth's gravitational pull downwards. That is equivalent to being out in deep space, way away from any big planet or anything like that, and accelerating at 9.8 meters per second squared. And any experiment you would do in this situation, you'd have to get the same result in this situation. And the flip of that is true. Being way out in deep, deep space, very far away from every planet, has got to be identical to being near the Earth, but falling freely in a gravitational field. So remember, Newton's big inspiration was seeing a worker up on a roof and imagining what would that worker experience if he fell off the roof while he was falling. Um, yeah, it's the principle of equivalence. The idea that gravity is not what Newton said it was. It's a force that objects have. Gravity is a curvature of space-time due to mass. So yeah, here is what one of the original slides looked like. So just quickly, light clocks and time dilation and length contraction. And remember the twin paradox. And here's the equivalence principle. We also talked about muons, E equals mc squared, how you can make nuclear weapons out of that. And then general relativity, relativistic stuff. General relativity. The weirdness of falling into a black hole, how mass curves space and time, gravitational lensing, things like that. So, yeah, crazy, crazy stuff. And then we started with the electromagnetism stuff. So, chapter 32 was electrostatics. So, what is the symbol for electric charge? At least one of the classes you might remember had a whole lot of difficulty remembering this rather basic fact about electromagnetism. Yeah, the symbol we use for electric charge, it's Q, little q or big Q. So there is Coulomb's law. The force electric is equal to that constant times Q1, Q2, divided by the distance between the charges squared. So what is the SI unit for electric charge? It is the Coulomb, capital C. And what is the formula for electric field E due to a point charge? It looks sort of like the formula for the Coulomb's force, F sub E. E is equal to KQ, that's the charge causing this field, divided by d squared. And there's Michael Faraday. And remember, Faraday is the guy who first came up with this idea of fields, which is philosophically a little bit weird. If you're dealing with the force, you're saying one charge is affecting another charge. If you're dealing with the fields, you're saying one charge is affecting space, and it's the space that's going to have the effect on the other charge. So it was a weird idea, but ended up being a very fruitful one and a very important one. So yeah, we use the idea of fields all the time now. So yeah, other things we talked about. Remember, it's Ben Franklin's fault. He, was studying electricity and static electricity in particular, and he figured out all the things that have one type of charge and all the things that have another type of charge, and he named them, and he took a shot just based on nothing, called one positive, one negative, and it really would have worked out better if he had named it the other way. So yeah, we dealt with that stuff. We also did this stuff, unit vector notation and angle notation and this stuff. So yeah, I know if you go on to take the physics, especially the calculus-based physics in college, hopefully that stuff will stick with you, because being able to do that, it's tricky stuff. And if you guys have seen that before, my very sincere hope is that when you see it again, you will really have a leg up on the other people in your class. So yeah, unit vector notation, angle notation, important stuff. So on to chapter 33, electric potential energy and electric potential. So what are the symbol and the units for electric potential energy? Well, it's an energy, so its units have got to be joules. So yeah, we call this one EPE. Its units are joules. So there's your formula for the electric potential energy between 2 point charges. And there's James Prescott Joule. And what are the symbol and units for electric potential, which again has a very similar name, but is not at all the same thing? It's V, or delta V. Its units are volts. So there's volts right there. And there's your formula for the voltage due to a point charge. So what are other names for electric potential? There are lots of them. So yeah, you can call it electric potential. That would be V. You can call it electric potential difference. That would be delta V. You can call it potential difference, potential, voltage, electromotive force, or EMF. So yeah, stuff we dealt with in this chapter. Electric potential, the voltage due to a point charge. Electric potential energy can be positive or negative in different situations. Remember, we did this fun lab. This is Ben Migliori's lab. Hopefully, you guys enjoyed that. I think most people enjoyed parts of it, even if other parts got a little tedious. And we also started to learn about capacitors and QVC. Q equals V times C. And so here's your formula for capacitance, electric field between two parallel plates. And this is the law of conservation of energy, the first law of thermodynamics. And this one, which was the bonus question on 2 separate tests, and I don't think anyone actually got it on either one of them. So shame on you, or shame on me for not teaching it better. This is the work energy theorem. So it's equivalent to this one. You're just thinking of work and potential energy differently. So in the work energy theorem, you're thinking of potential energy as the opposite of the change in internal work. It's weird. I don't like the work energy theorem as much as I like the law of conservation of energy, which I like very much. It's a very one with everything idea. So on in chapter 34, electric current. What is conventional current, or just current for short? When we talk about the current, we talk about positive charge moving in one direction. So yeah, I is your symbol for current. It's units or amperes. So it's change in charge over change in time, or if you're real calculus-wise, it's the derivative of charge with respect to time. So yeah, current or conventional current is the direction of positive flowing charge, or it's the rate, and the direction is important too. It's the rate of flow of positive charge. So what actually flows through a wire? Yeah, it's actually the negative charges. The electrons are the things that do the flowing. So yeah, this is the thing that Ben Franklin guessed wrongly on, and we're kind of stuck with it. And fortunately, it doesn't often matter. You don't actually really have to know which one is doing the flowing, but it would have been a little bit easier if Ben Franklin had guessed it correctly. Still a good guy, Ben Franklin. But on this particular thing, he got it wrong. So, what is Ohm's law? Hopefully, you can remember this one. This one came up a lot from this chapter onwards throughout the year. V equals IR. So there's Ohm. What is Watt's law? So Watt's law, you may not know it as well by name as you know Ohm's law, but it's the one that goes with Ohm's law. It's PIV. Power equals current times voltage. And then we also talked about alternating current and direct current. So who was it that liked the AC and who was it that liked the DC? Tesla liked AC and Edison liked DC. AC ultimately won out. For things we learned in the last couple of chapters, it's better for moving electricity over great distances with fewer losses is the main reason, because with AC, it's very easy to use transformers to change your voltage up or down. So yeah, Tesla was right in this case. Edison was wrong. So yeah, in this chapter, remember we learned all of the water analogies. We learned about fuses and circuit breakers, resistance and resistivity, and the temperature dependence of resistivity. And we also talked about superconductors. So remember, superconductors are things that act pretty much like normal conductors at regular temperatures. And then if you get them below a certain critical temperature, all of a sudden the resistance just completely disappears. So yeah, it's totally a quantum mechanics thing. Superconductors. So chapter 35 was circuits. So how do resistors add in series? In series, resistors add just regularly. You just add them up. And how do they add in parallel? They add inversely. So if you got to use this formula, or there's another version of this formula too. Resistors add normally in series and inversely in parallel. And how do capacitors add in series and in parallel? Well, with capacitors, you flip the rules. So capacitors in series add inversely. That's what we have here on the left. And capacitors in parallel add normally. So yeah, we went through the whole derivation of those ideas. So how is analyzing a circuit like Sudoku? Well, first you have to use the clues you have, and then you figure out new clues. And then you take the new clues, and then you figure out even more clues, and you just keep going and going until you're done. And there's more than one way to skin a cat. You don't necessarily have to do it all in the exact same way that I would do it. But you're basically going to keep doing that. You're going to take what you know, you're going to use it to find some other piece of information, and then you're going to use that new piece of information to find more pieces of information. And you keep going until you're done. So yeah, remember, here's Kirchhoff. So we did KCL and KVL, the different things with the loops and analyzing circuits and all that stuff. And then if you have one of these situations where you have more than one battery in a circuit in different places with the different loops, you've got to build the system of equations and solve it for that because you have more than one unknown, all that stuff. So yeah, if you stick with the physics, that's something you're definitely going to see again in physics 2. And again, more than one way to skin a cat. So you don't have to do it my way, but my way works really well. So yeah, you'll see. And then 5, yeah, are circuit boards fun? The answer is yes, circuit boards are fun. So hopefully you had fun doing that circuit lab, and hopefully you learned how to use a multimeter a little bit. And they're worth picking up. Buy a cheap multimeter, and yeah, figure out different ways you can use it to see if a light bulb is good or if a circuit is complete, if it has what's called continuity, things like that. So yeah, hopefully you learned a little bit about using a multimeter. Practical information. So yeah, we learned about series and parallel and simplifying circuits and things like that. We also learned about shorts. So remember, yeah, if you have a short, you're going to get a huge amount of current. You're going to set the thing on fire. So yeah, don't have a short. Then chapter 36 was magnetism. What are the symbol, unit, and vectorness of magnetic field? So we've been using this one a lot lately. So hopefully you can remember this. Yeah, the symbol for magnetic field is B for whatever reason. Its unit is the Tesla, in honor of this debonair fellow right here. And magnetic field is very much a vector. So yeah, we had these different formulas for magnetic field. Here's the vector version, which if you take calculus-based physics in college, you're definitely going to have to know how to do it the vector way. But mostly we use this version. So we learned a couple of right-hand rules. What was the first right-hand rule that we learned? It was Ampere's right-hand grip rule. So yeah, if you have current flowing through a wire, hold out your right hand, put your thumb in the direction of the positive flowing current, and then the way your fingers wrap around your hand, that's the way the magnetic field's going to go. And what was the second right-hand rule we learned? This was the cross product right-hand rule. So again, the way I taught you this, there are different ways of thinking about this. I tried to go with what I thought was the most logical. Your thumb is still the direction of motion of positive charge. The direction of your other 4 fingers is still the direction of the magnetic field. And then your palm pushes in the direction of the resulting force. So yeah, when I was researching this chapter, came across a lot of different ways of thinking about this, and some of them even switched to a left-hand rule, and they keep changing what your thumb does, and you have to turn your fingers halfway through and stuff like that. I tried to go with what I thought was the most logical way. But yeah, you'll see this stuff again in college. So what is a long wire with many turns called? So if you have a wire and you just loop it around many, many times, we call that kind of thing a solenoid. So here's your solenoid formula. It's a way for getting a very intense and fairly constant, in terms of magnitude and direction, magnetic field in a certain region. So inside the solenoid, you're going to have a big magnetic field and not so much magnetic field outside the solenoid. So yeah, a very useful kind of device. And what do you get when you put an iron core inside of a solenoid? You get an electromagnet. So yeah, those are certainly useful for many, many things. So the final chapter we got through was chapter 37, Electromagnetic Induction. We got to it. We didn't really get through this chapter. But yeah, what needs to change? What needs to change to induce an EMF, an electromotive force, a voltage, in a coil of wire? The thing that needs to change is the magnetic flux. So the induced EMF, epsilon, is equal to minus n, the number of turns, the number of loops you have going around your coil, times the rate of change with respect to time of the magnetic flux, the symbol for which is phi sub b. So hopefully throughout your 2 years of physics, you learned quite a few of the Greek letters. Yeah, that'll come in handy if you join a fraternity or sorority next year or the following year, or at least start going to the parties. Yeah, the Greek alphabet. Great stuff. So what is the formula for magnetic flux? It is phi sub b is equal to b a cosine theta. So b is the magnetic field, a is the area of the loop, and if there were many turns, you would add an n to the front for the number of turns, and theta is the angle between the magnetic field and the line that is normal to the area. So if you start taking things like linear algebra and things like that, it turns out you can assign a vector to an area, and the vector you pick is perpendicular to that area. And whether it's going up or down is going to mean different things. But that's a linear algebra thing. So, yeah, many of you are taking STEM. If you go into physics or engineering in particular, yeah, you'll have to learn some of the linear algebra. It gets weird. And what are the units of magnetic flux? It's the Weber or Weber or Weber. I don't know how you say it. But yeah, phi sub b, magnetic flux. Also, it's a Tesla meter squared. And I think this is the last slide we have. Yep, it is. Sorry, I didn't mean to give away the answer. Yeah, what are the input and output of an electric motor? The input of an electric motor is electrical energy, and the output is mechanical energy. So you're going to run a current through something, and you're going to cause it to, mechanically, physically turn. You're turning electrical energy into motion. So what are the input and output of an electric generator? Well, it's just the flip. In a generator, you're going to take mechanical energy, so the energy of something that's actually moving, and you're going to turn it into electrical energy. So yeah, motors and generators go hand in hand in much the same way that speakers and microphones go hand in hand. They're just really flips of each other. So that's it. That is the last slide in this final parts of the slides, and therefore it is also the last slide in Physics 2. So I wish we had gotten through more stuff. Some of that was my fault. Some of that was beyond my control. But I really hope you guys enjoyed the stuff that we did get through. I definitely enjoyed teaching it to you. Yeah, I love my students. You're a very wonderful group of human beings. So best of luck to you guys in the future. Yeah, and I hope to see you in person at graduation. Please let there be an in-person graduation. And if not, maybe swing by for a visit next year.